Stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers, their job to redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. And today I'm pleased to have with me in the studio Kerry Bernstein, a program manager since 2012 in DARPA's Microsystems Technology Office. That's the office, among the agency's 6 technical offices, that is devoted to doing more with electrons, photons, and electromagnetism than has been possible in the history of technology. Kerry's curiosity in science and technology knows no bounds, but his background in the microelectronics industry has everything to do with the mission he has taken on at DARPA. More than anyone, he has been pushing technologies to reduce or even eliminate the vulnerabilities to our billions of microelectronics chips to things like hacking, counterfeiting, cloning, tampering, and other nefarious actions that are just no good at all for national security. Prior to coming to DARPA, Kerry, an electrical engineer by training, logged more than 30 years at IBM, where he worked on a dizzying array of technical subjects, including microprocessor circuit design, high-performance, low-power devices, circuits, and architectures, new technologies that could replace the basic logic switches that underlie almost all of chips today, three-dimensional chip integration, and the ways radiation can damage chips. Kerry has co-authored textbooks on circuit design. He holds 155 patents and is a fellow of the Institute of Electrical and Electronics Engineers. Kerry, it's my pleasure to have you in the studio today.
Oh, it's really mine. Thanks.
I'm always fascinated by the way people get interested in science and technology. If there was some transformative moment or a key person in your life that pointed you in that direction.
Ivan, it's sort of an accident, and it's one of the most fortunate accidents I've ever known. So even as a little kid, I was always just very interested in astronomy and astrophysics. And God bless my dad, he didn't understand any of the lectures, but I'd identify famous astronomers coming to lecture at the University of Chicago or University of Illinois, and he would take me. It was wonderful. And I went to college anticipating I would study astrophysics and astronomy. And I come from a family of fairly modest means, and it became very apparent that I needed to be able to pick up my college cost. And astronomers and astrophysicists just were not in real high demand at the time. So I looked around and my credits applied to electrical engineering and to normal physics. And I embarked on a career of engineering. And it was the most wonderful accident I've ever made.
Let's talk about that move you made, that pivot into electrical and really electronic engineering, as it turned out, right? So because you ended up going to IBM, one of the most storied companies and organizations when it comes to sort of the entire history of microelectronics. And I just would be interested in hearing about the numerous hats that you did wear there and kind of what you learned about that technology.
Timing is so much. And at the time that I graduated college, the technology that we use in current computing, CMOS, was just in its infancy.
And just for listeners who might not know that, that's such a familiar term if you're in that microelectronics world, but CMOS stands for what, Kerry?
I've always wondered that. I don't know. CMOS stands for complementary metal oxide semiconductor technology.
And this is sort of the workhorse technology that underlies pretty much any chip that any of our listeners might have in their computers or in many of their gadgets.
It is the predominant technology,
predominant
yes.
One. Okay.
Preceding CMOS field effect transistors was a technology called bipolar. But bipolar was very power hungry, and the power was really limiting how much you could do with it. So when I first entered the space, CMOS was just starting out. And I had the great fortune of joining IBM, and IBM was leading the field in the development of processes, circuit design, architecture for truly high-performance computing. And so over a career of 30 years, I enjoyed this incredible ride, bringing through new materials, new applications, producing the technology that went into machines that we used to play chess, to play Jeopardy. Quite a ride.
So there's two things about your experience there that fascinated me. One is that you became part of that IBM team with a bachelor's in electrical engineering, right? This was from Washington University in St. Louis. And then you got several PhDs worth of education while you were there, because you don't have a PhD here.
Ivan, I don't even have a master's.
Don't even have a master's, but when I see you in action, oh my gosh, right? Clearly you've got everything that any of the most hyper-educated people here have, but you learned it kind of in situ in the industry.
It was a matter of luck that when I entered the field, the industry was moving so fast that for me to take time away, to take time out to go for my graduate degree was actually putting me behind, because I was not getting to participate in all the game-changing new process and chip design technologies that were being produced. So I did take a few graduate courses, and at that point decided, no, I really want to be in on the ground floor stuff,
right,
and just never look back. I've been very fortunate to be surrounded by just incredible human beings. There's this notion of a rising tide raises all ships. And I've been so fortunate throughout my career to be surrounded by truly incredible human beings.
Right.
And that continues here.
There's one other thing that I think emerged probably largely out of your IBM experience, and that's your 155 patents. Who knows, by now, maybe this week you got another one. But tell me a little bit about some of the ones, say, that stick in your mind most, you're most proud of, or that perhaps had the most consequence.
Perhaps the one that sticks out in my mind the foremost is general purpose registers for high performance computing. At the time,
and you'll have to explain that for me and our listeners. What does that mean?
So clearly in thread parallel machines, there's simultaneous need for the same data in multiple locations in the microprocessor. And at the time, the notion was, well, let's keep interrogating a memory over and over and send its results to each of the separate places where it might be needed. The GPR, the general purpose register invention that I developed with our team, allowed us to simultaneously access the same data and send it to different locations all at the same time. And it found its way into a lot of very high-performance compute applications that follow to this day.
And when did you make this development and get this patent?
Early in my career. Is one of my first ones.
So sometime in the 80s?
Yes, late 80s.
Okay, so let's now move to your DARPA adventure. And another thing I really like to learn about from PMs is the mechanism by which you ended up getting here. So some met a program manager or an office director at a conference. Others just were in love with DARPA for years and years, and they kind of made the initial reach out. How did you actually end up here?
So without going geeky on you, over the 30 years that I was at IBM, this happened about 7 years ago. About 7 years ago, I was involved, of course, in the design and fabrication of high-performance computing elements. And it became apparent there was a class of defects, a class of failures that were exquisitely difficult to diagnose and very difficult to image or to try to define. But nonetheless, they impacted yield, they impacted performance, and in some cases even had the ability to change what the computer chip was supposed to do.
And so you're talking about defects that really go all the way down to sort of the micron scale, the transistor level, element level scale of these chips, right?
You're exactly right. And I'm not smart enough to be a high-level architect. I was very much a hardware engineer, very much about the hardware, the physical design and fabrication of the actual computer
right. And just
chips.
Again, to give listeners just a vision of this, I believe we're probably talking about defects that could be the size of like individual biological cells, 50 microns across, even smaller.
Indeed, indeed. And as technologies scale, the size of the defects that we're vulnerable to also continues to shrink. So it's essential to keep a very, very clean environment. So it became clear to me that there was a class of defects that we were vulnerable to, not just from a yield or functional point of view, but that potentially someone malicious could intentionally assert upon a process or upon a design to perhaps compromise the component or its function or its reliability, its lifetime. To make a long story short, I became a contractor consultant to DARPA And
was this consulting era or phase of your intersection with DARPA, was that to begin to define the kinds of programs that you ultimately would end up running with the aim of addressing the concerns that you learned about when you were at IBM?
Indeed. Initially, it was to consult on an existing program. And I became involved in actually doing things to computer chips. And then the DARPA program would hire reverse engineers to try to find what was done. And we continued to make progress at both detecting, identifying those features which could and couldn't be detected. And one thing led to another. And after about a year of consulting, DARPA finally said, why don't you come to DARPA? So I retired from IBM at that point and came to DARPA to assume the swim lane, if you will, the swim lane of hardware security.
Right, and at least 3 of your programs and the names of them really kind of reflect just some of the goals that you have had in mind and have been working toward. So I'm referring to Trusted Integrated Circuits, which is known in the short form as TRUST, Integrity and Reliability of Integrated Circuits, known as IRIS, and the Supply Chain Hardware Integrity for Electronics Defense, which is known in short as SHIELD. Each one has its own individual aspects, but together there's a certain kind of theme. And I'm wondering if you can actually sort of talk about them collectively and, of course, diving into each one as you might feel so inclined.
Indeed. God bless our warfighters. It is critical now for us to make sure that not just the mission is successful, but that we're protecting the warfighters executing that mission. The electronic components we use to support that mission need to be authentic. We need to make sure that those parts do no more and no less than they're supposed to, that they were built where they claimed to be, when they were claimed to be. We have to make sure that they last for the full stated lifetime. We have to make sure that there is nothing done to that component during the supply chain, during distribution, that there are no Trojan horses or Easter eggs, if you will, that are built in.
And this is challenging, right, Carrie, because in the creation of a chip, in the fabrication of a chip, there are so many players in so many different places that in some ways can have their fingers on it, that you really need some way of tracking all this.
That's exactly right. Once upon a time, chain of custody was a sufficient means of tracking the authenticity and the integrity of our components. But microelectronics has indeed become global. And right about the time that I warned DARPA that there could be an issue in this space, the electronics space indeed went global. The design is, we're not the only smart people in the world. And so because of this, it was critical that we develop those tools necessary to be able to confirm the integrity of the components we use.
One of the most audacious trajectories that you've been taking, and it just amazes me the progress that you and your performers have been making, is with tiny little chiplets about the size of glitter particles. I don't want to say anything more because I want you to tell listeners just what you've been up to with your performers on this task.
Before I even go there, I'm reminded that it's one thing to come up with a challenge, but it's quite another to go execute, to go accomplish such a challenge. And to be clear, the heroes in the space are the performers that DARPA has hired via contract to go solve this issue. I'm astounded daily, just the creativity, the amount of themselves that they pour into this effort. They skip holidays, they stay home over, they work through Christmas sometimes in order to deliver products such as those. The one that you're referring to, SHIELD, the threat space is large. The threat space of a microelectronic component begins in design. It goes right through fabrication. And then after fabrication and packaging, it goes through distribution. SHIELD is a taggant. SHIELD is a means of authenticating the parts that we use in our most sensitive applications. They have to be the correct part. For a number of reasons, the existing authentication technologies were necessary but not sufficient. So SHIELD is a microscopic taggant. We hope to get it into the world records here before we're all done. But it is used to make sure that this is the part that we intended to go into our defense systems. It has 5 special sauces. The first is a hardware root of trust. Every single microscopic shield chip has a unique identifier. The second special sauce that each shield die contains is an AES 256-bit encryption engine, 100,000 transistors on a chip that is 100 microns by 100 microns. The third is sensors that sense if the shield chip has been corrupted, compromised, cadoinkled in any given way. The fourth is an antenna, because it's way too small to contact. And so because of that, we have to talk to it with RF.
You mean physically contact, just too small.
That's correct.
Can't touch it.
The fifth is self-destruct capability, that if you attempt to remove it from the host component, it will cease to be functional. The part is powered by the interrogator. It is completely separate from the host component. The goal is that at any time, at any place, an untrained operator with no special equipment, in this case being just an iPhone or a smartphone, can test the integrity of their components at any time and place and get immediate, trustworthy results for free. Shield costs 1/10 of a cent apiece, and the entire operation would cost less than 1 cent every time you wish to authenticate the part. When you authenticate the part, it also reports the GPS location and the TCP/IP network address of where it was tested. In this way, at least for the most serious of our counterfeit and clone threats, we believe we have a very cost-effective solution. The goal is to make sure that counterfeiting and cloning becomes too expensive and takes too long for the bad guy to do.
Right. It's an absolutely amazing description. I mean, this sounds to me like about the highest of high technology. And certainly in the synthesis, the way you're mixing and matching different kinds of technologies also is just to me one of the things that characterizes a lot of what's going on here at DARPA.
One thing I'm somewhat of a pain in the rear to my performers about, because I'm just a knuckle-dragger hardware engineer, everything we do, you have to be able to hold it in your hand. And this is a program, especially this program, where it's not rainbows coming out of keyboards or unicorns leaping over terminals and magic will happen. This has to be deterministic, quantitative, very analytic, real engineering. And after the initial technologies were developed, SHIELD is about good engineering. We've engineered a beautiful product.
All right. Well, since you're all about that kind of ground truthing, where are we at with this program, with these tiny little chiplets? How would you characterize the status?
SHIELD is a 3-phase program. Phase 1 was to go develop those 5 core technologies because they really did not exist at that scale. All 5 have been demonstrated to be functional. Phase 2 is the integration of those technologies into the SHIELD prototype. Phase 3 of the program, which is the field testing of SHIELD, will begin early in 2018. The field testing is supported by some wonderful companies that we won't identify right now that have volunteered their supply chain. And we will do things to components with SHIELD attached and use their supply chains, and we will see how effective SHIELD is in catching compromises.
So, Kerry, we've talked about SHIELD. I do want to go back to 2 of the other programs that you've worked on. One of them is completed now, and one of them is still in progress. So let's start with Trusted Integrated Circuits, TRUST, which I believe is kind of one of the earliest programs you took on.
Yes. TRUST was the program that I actually began supporting before I entered DARPA. TRUST was a program to make sure that we could verify that a part is doing no more and no less than it is supposed to do. TRUST was a large program, lots and lots of achievements. We developed microscopes. We developed solutions for pulling net lists, if you will, the schematic from chips to make sure that the schematic is what it's supposed to. We looked at both COTS, commercial off-the-shelf product, as well as GOTS parts, government-owned components. We looked at field programmable gate arrays, as well as ASIC parts. The output of that program is installed in a number of agencies all over the country and is still being leveraged.
Right. And when you mentioned ASICs and field programmable gate arrays, again, those are just names for other kinds of categories of integrated circuits that have different capabilities, but all of which are in use today and all of which we really need to feel very confident about.
That is correct.
So that's trust, and that completed a year or two ago. When did that finish?
Yes, it concluded about 18 months ago.
Though obviously there's parts of the spirit of that program that are part of SHIELD. And the other program I just wanted you to say a little bit about, this one continues today, and that's the Integrity and Reliability of Integrated Circuits program, or IRIS.
The question that IRIS answered was, if indeed we know that this component has not been compromised in its function, can we still be assured that it has not been compromised in its integrity? How do we make sure with a low sample size that this component indeed fulfills its lifetime spec, its reliability spec, that it is up to the task of performing for 20,000 power hours or 100,000 power hours or whatever the spec is, that mission that is critical to the defense system that it's installed in.
Okay, and this is to defend against such things as, a counterfeiting practice where an old chip might be taken out of some unit. It might then be blacktopped, right, where a new kind of packaging is put on with new printing. It looks new, but in fact it's old and so might not be able to actually live up to the spec that a user expects.
That's correct, Ivan. Just like human beings age and automobiles rust, there is a lifetime to electronic components, and the lifetime must be, we depend on that lifetime when a system is built for that part to execute its function. Even without the malicious intent, we need to be able to very quickly assess the reliability of a part. And currently, the reliability science is a very involved, painful, long-term goal. And so IRIS looked to try to improve the turnaround on the testing for reliability.
Okay, so I want to move to a couple of other questions before we close out. One of them is really, I want you to reflect a little bit about microelectronics as a technology and your role, your several decades role in pushing that technology forward and doing whatever you can to ensure the integrity and safety of it. And, with some programs even moving forward, thinking about next generations of microelectronics devices, even in the nanoscale area, so that we continue to have a progressive technology in microelectronics. Just as you think about all of that, what excites you about this category of technology? And, Kerry, what concerns you about it?
Ivan, a few months ago, I had the privilege of spending a week with the 311th Fighter Squadron at Holloman Air Force Base in New Mexico. And after spending a week of them sharing with me what they do, I had the opportunity at the end of that week to describe to them what I do. And that's when it hit me. My son is training to be an A-10 fighter pilot, the Warthog. And when I got in front of the audience, they all looked like Mikey. They all looked like my son. And it's hard. It's even hard now to talk about it. But it's not just as a DARPA program manager or as an engineer, but as a parent. How many people, everyone of course wishes the best for our warfighters, but how many people actually are in a position to do something about it? It was one of the greatest epiphanies of my time at DARPA, was to realize that I've been trusted with all this resource and funding and security and given everything I need to go do what I know needs to be done. If I fail, it's my fault, because God bless this agency, it's given me everything I need to succeed, and it's all on me. And that's what's driven me. And in front of an audience like that, they deserve no less.
Well, thanks for that, Kerry. You've been here since 2012. So you've been here longer than a lot of program managers, and you probably are coming toward the tail end. When are you leaving?
September of 18.
September of 18. So I'm not actually sure you're even going to be able to see SHIELD through all the way to the end. I know that you're going to go most of the way, but I imagine you're going to be handing off some of the final testing. I'm just wondering, with 6 years of participation in this agency, which is part of the innovation ecosystem, what you have learned about it as an organization and as a culture in technology.
DARPA is an incredible place, just an incredible place. Of course, it's a human organization, so it's given to all the variation that human endeavor introduces, but it's such a rare place. To be given the opportunity to go develop those ideas, which can be made to work, is a once in a lifetime.
Do you have any thoughts about a post-DARPA phase of your professional adventure?
There are certain capabilities this nation urgently needs, and I'm pouring the concrete in those holes as quickly as I possibly can. My intent when I complete my DARPA post is to be able to move into a position where I will be allowed to continue to pour that concrete.
Well, I, for one, will be excited to watch you as you take your programs through to the point that you will be able to, and to see what you do when you leave here, now bringing your DARPA experience perhaps back into the private sector and industry, whatever you might do, and for which I wish you the best of luck. So we are at the end of our time here for this podcast. I just want to thank you for spending this time with me.
Oh, thank you, Ivan. It's been a pleasure.
And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. For more information about Kerry Bernstein, the programs he runs, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download this podcast, go to the Voices from DARPA page on DARPA's website.